Thank you very much for attending. So yeah, just a quick introduction. Darren Wilkinson, Managing Director at VEXO. So really, what was the purpose of this study? This kind of went all the way back to 2018, and VEXO and myself submitted a hypothesis to Loughborough University. And that was on the back of years, and almost 30 years in the industry in water treatment and building services, whereby, we understand, anecdotally at home when our radiators, they get cold spots, they get pinholing, and of course you have to replace things much quicker. But of course, especially in an energy crisis as well, kind of what's the relationship between that poor water quality and energy? And there's very little out there really that's engineers can use as a sort of a benchmark. So that was really very much what sort of spurred this on. But not just in the commercial sector, also opportunities for homeowners to be educated as well. We want to get to net zero or zero carbon, globally, but what are the quick fix measures maybe we could do? Actually quite simple. So this is the purpose of the study. So into understanding the true impact of water quality, a survey found that 76% of building managers that were surveyed experienced some form of corrosion in heating and cooling systems. And a third of all those that were surveyed have indicated a high or very high financial loss or losses due to that corrosion. So maybe some of you have been involved on projects, for example. I'll just giving some anecdotal examples. Belfast Hospital, it was in the press some years ago, cost into the millions. It was a new building, had all sorts of problems and had to vacate whilst that was remedied. Arcadia in London, in Oxford Circus, had to vacate the building. They had problems with ammonia that caused issues with stress corrosion cracking, and again had to vacate the building. So there's been projects as well where some of the new technologies, if the water quality isn't maintained correctly, can cause all sorts of problems as well. In the US, financial losses, believe it or not, can exceed 276 billion, or 3.1% of gross domestic products for the country. That's not just closed loop hydronics, that's across all industry. And during the experiment, crash test dummy experiment, as it were, we went through 3 pumps. So it gives you an idea as well of the life cycle impact it has on components, particularly when we're trying to understand and measure embodied carbon within a building. So inadequate maintenance of the water quality ultimately can significantly reduce the life of the plant and equipment within those systems and certainly increase the embodied carbon. So we want to investigate that further, and how do we calculate that? So first of all, let's understand the sources of water impurity when we're looking at filtration. Essentially, dissolved oxygen is a big problem for closed loop systems. So systems that are having leaks, for example, systems, let's say, that are being drained regularly for whatever reason, maintenance reason, a lack of understanding, dissolved oxygen is generally a big problem for corrosion. Dissolved minerals, so in hard water areas where we are making up or we are having water losses on those closed loop systems, scale forming minerals will want to precipitate out under temperature, so particularly in heating systems. You may have come across that, in your homes perhaps, banging boiler syndrome as it's known, scale forming on the heat exchanger. And particularly with the newer technologies now, and we're looking for energy efficiency, if we don't look after the water quality, we're adding that dissolved mineral onto the plate heat exchanger, we're going to be using a lot more gas. Suspended solids, they can come as a result of corrosion. Sometimes they can even find their way into the system from the leaks. So particularly new projects, when you're filling the system, you might be putting quite a lot of sand and debris where it's a new mains water pipe connection that's been run. And then microbiological activity. This is going to be a big one for the industry, I think, as we move towards lower operating temperatures, as we move towards the use of heat pumps. Corrosion rates increase with temperature. Whereas we're lowering the temperature, but we're now kind of moving more into an incubator scenario whereby bacteria will become the problem. And believe it or not, bacteria, biofilm, which they create, this kind of like horrible slime, is very much a thermal insulator as well. So that's going to cause problems. So that's something we need to watch out for. But ultimately, those things all lead to corrosion. And with the scale, all of that leads to plant damage. But ultimately, the net result can be plant failure and increased energy use. And it always happens at a time when you don't want it to. So normally, we always find in the industry in October, it's getting cold, let's get the heating on. Oh no, pump seals have just leaked. Oh no, we've got radiators bursting. Oh, the building's cold, I'm freezing, the fan coil's not working. So there's a lot to it that you end up paying for in the long run. So how do we sort of replicate that? You know, how do we create that in a lab scenario? So we looked at methodology and the design of the equipment. And so here you can see a picture of the rig that was built, which is our mini closed-loop hydronic heating system. And you can see it just to sort of show you. So here we've got a 1 kilowatt electric heater. As we come along here, we've got a regulating valve. We have a strainer here. By the way, this is all in stainless steel. And then we come along and we've got a Velo Stratos smart pump here. So that's great because that gives us quite a lot of data, as you're probably well aware. And then as we head up this way, we can send the water and direct the water wherever we would like to go. But for the purpose of measuring, we've got water quality, if you like, mechanical filtration devices here. One is an inline and one is a side stream. And we also have the possibility here between these flanges to change the materials of pipework that's being used. So actually we can do a lot of analysis and understanding failure and corrosion as well. So depending on how we want to test the equipment as well as the materials. Some connections here as well we have where we're able to connect this to, which you'll see later on, we have a rig that measures the chemistry as well. There's some analytical chemistry that's being monitored as well at the same time. Pressure vessel, and then we make up and we monitor the pressure and we make that up with mains water. So the rig is actually 18.45 litres in volume. It's the 1 kilowatt heater inline. For the purpose of the experiment, we maintain the temperature at between 50 and 55 degrees C, purely really from sort of a Legionella perspective, more importantly, scalding, and you can imagine trying to operate on the rig, which Amir Sullivan, who put the white paper together, wanted to make sure you didn't scald yourself. A lot of time spent with the rig. And then we had to look at flow rates and we had to look at pressure. So the flow rate is controlled by the pump primarily, but it's also validated by the monitoring unit. So for the purpose of this study, we had 3 flow rates that we focused on, 2 meters cubed per hour, 4 meters cubed per hour, and 6 meters cubed per hour. And the system pressures were also tested at 3 intervals, 0.5 bar, 1 bar, and 1.5 bar. So therefore, the various pressure and flow rate conditions will be tested against each other to establish a correlation between the system filtration and the pump power consumption. So at this stage, this is early stage of research, but at this stage we're just really looking at the electrical consumption of the pump. There is a piece that we're going to be doing and talk about a bit later, but in terms of actual gas usage as well when it comes to water quality. So we had to replicate corroded or poor water quality systems. So as per the Belgium Scientific and Technical Centre, we took information from their literature, 4,000 grams of magnetite or rust or hematite per 1,000 litres per year. And then 800 grams of magnetite powder was used to replicate a system corroding for over a period of 10 years. And let me tell you, I'll get some photos, but there are systems that fail much sooner. And then to maintain realism, actual magnetite powder we actually used to replicate the corroded system. That being said, there are other things such as non-magnetite that can be within systems, but for the purpose of a heating system trial. So the sequence and testing. So we thought about how do we want to run the testing. So step one was we started with a clean system. That was really to give us our control, as it were. Then we ran a dirty system scenario. And then we filtered, and then we turned the filter off. And all flow rates and pressures here, we've in accordance with CIBSE Guide B and ASHRAE Handbook 2021. So the results. So under those 3 different test conditions, we found that the 1 bar was actually more efficient in the operating condition, and the dirty system actually increases the power consumption by around 30%. So that's a significant amount of load suddenly being added to the pump that's not been designed for. We found the filters effective in restoring the system efficiency. We then looked at the power consumption based on 1.5 bar, or 217 psi for our American colleagues as well. So under this, 1.5 bar does show there's not much in terms of energy savings, as will be shown by the thermal imaging shortly. And then we found at 0.5 bar, the dirt increases the power consumption of the pump by 200%. The filter is able to restore the system efficiency by 50%. However, the power consumption is still 100% less than the original clean condition. So why does turning the filter off use most power. So obviously you have to imagine we've run different conditions of adding magnetite, adding essentially detritus into the system. So on the left image, please, by the way, ignore the actual temperatures as well. They've just been magnified essentially as part of the test, but it's all relevant in the paper. A thermal image of the clean system before the addition of magnetite powder. And actually, again, let me just use this correctly. So what we can see here, these hoses are what go off to the monitoring equipment, the chemical monitoring equipment. So you can see we've got good temperature running through. And then obviously a thermal image of the dirty system, we can see that these hoses are actually blocked. So where we've got a hose here, there's actually nothing going through that. And that sort of replicates, again, it's a small volume system, but it does replicate what occurs in live buildings, commercial buildings. You know, you start having blocked pipe work, fan cords that block and so forth. To sort of show you that under different conditions, what that looks like in terms of efficiency. So we actually broke it then down. Rather than throwing all 800 grams, we started with 400 grams, which is actually on the right-hand side. And what we found was in terms of the filter's ability to remove the level of magnetite, as one would expect, the more we put in, the higher the level of saturation we're seeing on the filter. Basically, the filter's going to block much sooner than that of half the amount of magnetite. So it was really labeling the importance of maintenance as well. So it's one thing saying, yes, I've designed a system, I've got a filter on it. How do you know if it's blocked? Because actually the impact, and the next images I'm going to show you, are what comes when we don't maintain the filters. So thought I'd pick out probably the worst I could find. So luckily nobody's had lunch yet. So these, just to give you an example then, and these are obviously we have, at VEXO we have hundreds and hundreds of various types of photographs of systems. This is actually from a piece of pipe work in an old school. So you can see it's good thick steel, but based on the flow rates, things are wanting to settle out. And you can actually see here, the two differences in colour is magnetite and hematite. And that indicates straight away that they've been, running a lot of water, so they've got a lot of leaks, which we knew they did have. So it leaks, oxygen equals corrosion, and obviously equals scale. So this is actually the same, just for the purpose of this is actually the same system, both the left and the furthest right. In the middle here is actually from a university, and that was their closed-loop heating system. So you can just about see somebody's hand there, and what he's actually holding there is a magnetic block. So this is a combination. What we've seen here is actually magnetite. And I mentioned biofilm earlier. So there's actually a combination of biofilm sitting on the surface. And the reason for that is not being maintained. The filter wasn't cleaned as it should have been. So you can see that we've actually still got the filter, the non-magnetic filter under here. But this biofilm has started to occur under that stagnant condition. So stagnation is a big problem for systems, closed-loop systems. So what we found, the key findings were, certainly by filtering, we reduced the power consumption that the pump was using. Higher the pressure, more effective the filter is at collecting the debris. And as I say, remember these are amplified because this is a rig. The system pressure at 1 bar was able to restore system efficiency back to its original state. And that high pressures can lead to filter saturation, leading to increased energy consumption. Thus, the filter will need to be changed. Now, in reality, we went from 0.5, 1 bar, to 1.5 bar. Most commercial buildings, unless your plant room's on the roof, you may be just over 1 bar, potentially. But in reality, a lot of commercial buildings are well over 1.5 bar. So what we'll find is that you'll actually be releasing and capturing a lot more debris in the system through your filter. Thermal imaging was also used, and it's an effective methodology to employ. So if you want to identify pipe blockages and filter saturation. And then when we introduced the magnetite powder, under low pressure, the pump consumption increased by up to 150%. So basically, water quality leads to plant failure, but also has an impact on embodied carbon costs. So just before I acknowledge that, I mean, but keeping in mind, in the laboratory situation, we were using the system pump for the filter, for the side stream filter. So of course, there's an element of consumption of power that we're using to push it through the filter. So in any case, as that filter starts to block, we're going to be using more energy as well. But if you look at that as a multiple across various pumps within a closed loop system, it's not just the one pump. So certainly savings. But I'm mindful of time as well, but just to wrap up, just to thank and acknowledge, as we have on there, all those that have been involved in the project or stakeholders. Any information is within the white paper, any technical information you want to look for as well. Any questions? Thank you.